After tuning the model hyperparameters through grid search and the use of the Optuna library and performing validation, we move to phase 3. In phase 3, the models are finalized and a copy of each model is trained on each of the 6 feature subsets identified using all training instances. Each of these models was then used to make predictions on the testing data and checked for accuracy. The naive Bayes model is simple and has no parameters to tune. The k-nearest neighbors model was trained with 11 neighbors, uniform class weighting, and Manhattan distance. The linear support vector classifier was trained using C equals 3 balanced class weights and a squared hinge loss function. The random forest classifier used 750 estimators, balanced subsample class weights, a minimum leaf sample of 2, a minimum sample split of 12, and a Gini score criterion. Because the different feature subsets contain differing numbers of features, a neural network was trained for each input size. Additionally, networks were trained with both hand-tuned and Optuna-tuned hyperparameters. The hand-tuned network used for the first 5 feature sets is a sequential network with 4 densely connected layers and an output layer. The hand-tuned network using the optimum features identified by the random forest is also a sequential network with 4 dense layers and an output layer. The only difference is in the size of the input layer. The Optuna-tuned model for the first 5 feature sets is a sequential network with dense layers and a dropout layer following each, ending in an output layer. The Optuna-tuned model for the random forest optimum features is a densely connected sequential network with 4 layers followed by dropout and an output layer. Finally, the Optuna-tuned model for the full feature set is a dense sequential model using 2 layers with dropout and an output layer. The feature subsets used are those identified by information gain, the ANOVA test, variance threshold, mean absolute deviation, and correlation coefficient. Each of these contains 20 features. Also tested are the optimal features identified by the random forest, which includes the top 50 features identified by feature importance. Here we see the final results of the test predictions. The Optuna-tuned neural network trained on the optimal feature set performed best at 75.3 accuracy, with the hand-tuned neural network performing almost as well. The Optuna-tuned network also scored above 70% using the correlation coefficient features, and the k-nearest neighbors model scored above 70% using the optimal features, as well as those chosen by information gain and correlation coefficient. The precision of most models using most feature sets is between 70 and 80%, with the random forest optimal features faring the best. We see lower recall scores, but both versions of the neural network using the optimal features score above 75. We also see that the k-nearest neighbors model scores above 70 recall using the random forest optimal features, correlation coefficient features, and also the information gain feature subsets. The weighted average F1 scores look similar to the accuracy, with the neural networks and k-nearest neighbors using the optimal features coming out ahead. Again, we see that the k-nearest neighbors model also performs well here with the information gain and correlation coefficient feature subsets. Confusion matrices for each model test predictions give a better idea of each model's ability to predict individual classes. As we have seen, the neural network models using the optimal features perform best, and the Optuna-tuned model does almost as well with the correlation coefficient feature subset. The k-nearest neighbors model does nearly as well as the neural networks, scoring above 70% with the information gain, correlation coefficient, and the optimal feature subsets. In conclusion, we have seen that the machine learning algorithms are capable of classifying types of network activity by learning from network traffic data. The normalized confusion matrices suggest that even those classes that were underrepresented in the data could be accurately predicted by some models given enough examples. Artificial neural networks performed best in these tests, but the k-nearest neighbors model performed almost as well, suggesting more study of the nearest neighbors model may be useful in this domain. Many of the network traffic features seem to contribute very little to the accurate classification of activity type. The 50 most important features identified by the random forest performed better than the smaller feature subsets and also the full set. Interestingly, the information gain and correlation coefficient feature subsets performed nearly as well as the optimal set using the k-nearest neighbors model. We also see that hyperparameter tuning using the Optuna library can produce better results faster than hand tuning via grid search. Directions for future work include gathering more data. A model cannot predict behavior it hasn't seen, and these results suggest that some of these models could accurately predict those underrepresented classes if more data were available. Exploring ensemble methods may also be profitable. Some of the model feature combinations tested here were more accurate than others in predicting the underrepresented classes. Combining these models may improve the overall accuracy. During this project, I've accomplished my primary goal of comparing the effectiveness of various machine learning algorithms in learning network traffic behavior and classifying type of network activity. I've also achieved my secondary goal of increasing my knowledge and experience of using machine learning methods, specifically artificial neural networks, and I learned to use the Optuna library for optimizing hyperparameters. Thank you.